Okay, YouTube, this is my second video in my module on kind of populations versus, samples, as well as kind of making hypotheses about entire populations based on sample data. And so as we get into kind of the second part of this module, we'll look at hypotheses about an entire population. And really, we say that in statistics, a hypothesis is a claim about a characteristic of a population. So this should be a hypothesis here. Sorry for the typo. But basically, as an example, hypotheses that we could make about an entire population might be these two that you see here. We say that a drug company claims that patients using its weight loss drug lose an average of 24 pounds in the first 3 months. And so, that kind of a claim about an entire population, we're not going to be able to collect data on everybody to gather a census of everybody with respect to that data, probably. So what we're going to do is we would form, like a sample of data and try to draw conclusions from that. Likewise, if I'm a medical researcher, I claim that the proportion of U.S. adults living with one or more chronic conditions, such as high blood pressure, is almost a half, like 45%. And so that's also another bold claim. And so in this video, what we're going to be doing is looking at what a hypothesis, I guess, is, which is this claim about an entire population, but also how to either, reject your claim or maybe accept your claim based upon experimental results. And so taking a look at that kind of idea of what we want to do here, it says to analyze a hypothesis, what we would do is need to distinguish between results that can easily occur by chance and results that are highly unlikely to occur by chance. So we say one way to analyze a hypothesis is basically to perform what we call a simulation, okay? And so simulations, basically we say when results are highly unlikely to occur within a simulation, then the hypothesis that you're making is probably not true because your simulation just basically doesn't support your hypothesis. And so a simulation, just to be clear on this one here, can be collected data. And so basically, when you look at running a simulation here, that doesn't mean you have to have some computer-based thing that you've done. It could mean that, for 8 weeks you paid attention to the weight of 20 people, and we would count that as a simulation. And if you had like 5 different groups of 20 people, that'd be really great because you're running 5 simulations. Hopefully that'd be cool if you did at the same time. But you could see how they compare with one another. And so simulations here, we're going to collect this data and basically based upon the data from our simulation, try to form this idea of whether or not these claims that we're making about everybody could possibly be true or not based on sample data, based on statistics to make ideas about parameters. And so let's take a look at a very specific example in this video. Now, when in terms of analyzing the hypothesis example down here, we're going to take a look at that here in a second. But before we move on here, let's look at a term that I want to be very familiar with. And basically, this term is or phrase here is a population proportion. And when you hear proportion, another way to look at a proportion is overall percentage. And so you could look at like a proportion, make a little note here, is the overall percentage of something, okay? So we'd say like if everybody, it's 50-50, you're born male or female, then you would say that the proportion of the population that is male is 50%, and the proportion of the population is female is 50%. So when we talk about a population proportion here, I should have subtitled this or titled this population proportion and sample proportion because I want to distinguish between the two. We say that a population proportion is the ratio of the members of a population with a particular characteristic, okay? And so, maybe we say that are over a certain height or within a certain range on their weight, okay? But to the total members of that population. So we would say that if I wanted to find a proportion of a population that satisfies a given characteristic, then what I would do is just pick out all the people that have that characteristic and divide by however many people are in the entire population. So like, what's the population proportion of, females who are Republican? And so we would just say, well, how many female Republicans we got here and what's the entire population? We would divide that out. And so we would get a population proportion, which would be interesting because you could kind of look at that as a parameter there because it's describing everybody. Now again, when we talk about population versus sample, remember sample is more prevalent because we're not likely to get the population data unless it's a smaller population. So we say a sample proportion is the same as a population proportion, but basically is the ratio of members of a sample of the population with a particular characteristic to the total members of the sample. And so you can see here that when we write a sample proportion, basically we're saying, okay, well, all the female Republicans in just our little sample of females here divided by the total number of females. You could get an idea of of that proportion of the overall females that would be Republican. And so that being said, it's going to play into our next example here. And basically this example I feel is a pretty good one for kind of describing a situation where you would either accept your hypothesis or reject your hypothesis. And so let's kind of take a look at this here. We say that you roll a 6-sided die 5 times. And so here's your 5-time roll here. And you do not get an even number. So basically, maybe you roll a 1, a 3, a 3, a 3, and a 5. I don't know, I just made this up. But basically, look at this. You didn't get any even numbers. And so the probability of this happening, we can look at that as the probability of basically not getting an even would be getting an odd, okay, times itself 5 times. And so we could say that, 5 odds in a row, 1 over 2 to the 5th, it actually comes out to be this percentage right here. And so basically, theoretically, we should not have this happen, or at least get no evens out of 5 rolls here, only 3% of the time, which is really, really small. So basically, we say then maybe we're suspicious that this die somehow magically favors odd numbers. And I know that that's a crazy thing to say, but basically, based upon the evidence, we could say that the evidence is supporting that this die is something wrong with it. So maybe we make this conclusion, but it says that the die maker claims that the die does not favor odd numbers or even numbers. And the die maker's like, well, it's 50-50, chum. So basically, what should you conclude when you roll the actual die 50 times? And maybe we get 26 odd numbers. And what should we conclude if we were to roll the die 50 times and get 35 odd numbers? Okay, and so basically, here's what I want to start with. We're suspicious of this die, but what you notice is what we're going to want to do is collect a sample of data and base our conclusions upon what we see happening in the sample. So when we look at this here, it says that the maker's claim or hypothesis, and this is the maker's hypothesis here, is that the die does not favor odd numbers, nor does it favor even numbers. So basically, this is kind of the same as saying that the proportion of odd numbers rolled in the long run is 50%. So basically, they're kind of saying if it doesn't favor one or another, again, it's 50-50. You're going to get 50% of the time even numbers, 50% of the time odd numbers. So they write here, so assume that the probability of rolling an odd is 50%. Basically, what we're going to do is simulate the rolling of the die by repeatedly drawing 200 random samples of size 50 from the population. And so this sounds crazy. Like basically what I would be telling you to do here is this. We would say in the entire population, okay, of samples of size 50. So this consists of all samples of size 50, every single one ever. What we're doing is we're grabbing out of here like 50 of these, okay? So like we're just grabbing all of these samples. And so basically what we're going to be able to see is what, I guess, proportion of the entire, 50 rolls here was even or odd. So in this example, we're going to say let the population of ones represent the event of rolling an odd number and basically make a histogram of the distribution of the sample proportions. Now, what you're going to see over here, and I'm going to describe this to us here, and we're going to take a look at it, but it's something that we would have used a computer to simulate. But basically what you see at the top is it's a simulation, and it says rolling a die 50 times. And so basically what's been done is this. We've performed a simulation where we've rolled the die 50 times. That's just one simulation. And we look at the percentage of overall things here. Notice at the bottom here, the percentage of overall rolls out of 50 rolls that resulted in an odd. And then we do this experiment again. We do it a second time. And we say, okay, well, what percentage there of overall were odd? Was it close to 50%? And we do this again. And we do this again. We basically roll it, 50 times, 50 times, 50 times, 50 times, 50 times. And we do this 200 times, you guys, 200 times. Every time recording what percentage or what proportion of the overall 50 rolls that resulted in an odd number. And what you would see here is this distribution like this, where if I'm explaining this to you here, we say that our relative frequency is over here on the left. Another name for a relative frequency, of course, is the probability. And so I'm going to write this over here. And I'm going to write now down at the bottom, it says the proportion of 50 rolls that result in odd numbers. But this was out of 50 rolls. And I think that we should mark this down here because what I want you to see is basically this. If we were to record what percentage of each of these 200 samples was overall resulting in an odd number, we would say that 50% of the time we should have odd number and 50% of the time even number. And so our kind of our average here, theoretical probability would be exactly 50%. And you can see that that happened more likely than anything. Exactly, I suppose we could mark here, this would be 25 out of 50 rolls here. If you were to roll that die 50 times, you would expect to get 25 of them be odd. And so what we're just basically saying here is that, of the 50% of the rolls should be odd. That's 25 total rolls here. But you can see that that happened a lot. And as you go away from this middle portion, we kind of get this almost, you could assume, normally distributed thing. And so you could see that 30% of the time, just to show you here, 30% of 50 rolls. That would be, 10% would be 5 times 3 here. This would be 15 rolls here if we're doing this in rolls. And for 70%, I can tell you that that's 35 here. So basically, when we look at this, we're saying that, is it likely that out of 50 rolls, you're going to get 15 of them be odd? Exactly 15 of them be odd, or 30% of them be odd. And you can see that that rarely happens. Most of the time, it's going to be somewhere in the middle of our distribution here. And so the two questions we were trying to answer were, hey, what should you conclude when you roll this die 50 times and you get 26 odd numbers? And so basically, here's what we've got. And I'm going to write this down here. We say hypothesis. Hypothesis. Rolls are 50% odd. And basically, we're going to say, well, then the 50% even. But basically, we're focusing on the fact that rolls should be 50% odd. And so when we roll this die 26 or 50 times and we get 26 odd numbers, what we're going to look at is our sample proportion. And basically, what we're saying is, this is in our sample of 50 rolls here, how many of them were actually odd. And when we get 26 divided by 50 here, I'll go ahead and get my calculator here. Basically, we're saying what proportion is 26 out of 50? 26 divided by 50 is 0.52. And so I'm going to write this down here. Basically, looking at our distribution over here, we would say that, is that close to 50%? Is that close to what the hypothesis is? And 52 is really close. And you can see that even on this image right here, that 26 odd numbers occurred more than anything, even though theoretically it should have been 25 odd numbers. But you can see that it's near this average, I guess, expected number of rolls here. And so 26, I would say that if the maker's saying that it's 50-50, okay, I know that I started off with 5 odd rolls here, but basically now I did out of 50, I got 26 out of 50 were odd. Then basically what I might do is accept the hypothesis. If this is true, if close to expected value of 50%, okay, then accept the hypothesis. Accept the hypothesis about the entire population that is true here. And their hypothesis basically was that this, I guess, die is fair. So now in letter B here it says, what would you conclude if you rolled this die 50 times and you had gotten 35 odd numbers here? And so what we're going to look at is the sample proportion for this sample of 50 rolls, where we rolled this die 35 times out of 50 times, got an odd. And so what we can see here is this actually is 0.70. And I want you to see that this proportion right here, looking at our distribution, okay, 70% of the time, or 35 out of 50 rolls here, were odd. You could see that there isn't even a bar here, which means you did this experiment, guys, 200 times. And out of all 200, no times did you ever get 35 odd numbers. And so since we're expecting to get around 50, you can see that the further we are from the kind of this average value, or this really high set of bars here, expected value, we're going to say the less likely it is to occur. And so what I would tell you is, if I had a die, I'm just saying, where I rolled it 50 times and 35 of them came out to be odd, I might reject the maker's claim, reject the hypothesis. So we're going to write reject the hypothesis, but we're going to write the maker's claim in parentheses, because the maker's claim was that it should be really 50% of the time should be, odd. And here you are getting this out here. And so I'm saying, I think that your die is not fair. And so, I have this little note down here. It says in example 3b, which is the one we just considered here, where we got 35 odd numbers, that'd be crazy. But we could see based upon the evidence here. But we'd say, you concluded that the maker's claim is probably false. Maybe that it's not fair. So in general, what we say here is that such conclusions may or may not be correct. That is to say that we're human, and sometimes we make mistakes. And so what we could basically come to the conclusion is, the way we could sum this up really is in a table here that we describe the 4 different possibilities that we could come to when it comes to making a decision and whether or not you're right or wrong. And so what you're going to see here is this. We have 2 rows and 2 columns in our table, and in each of these we say that our row values indicate what kind of a decision we come to. Do we decide that the hypothesis is actually true, or do we come up to the conclusion that it's false? And when we talk about the truth of the hypothesis, this would be like if you actually knew, like you could say 100% it was true or it was false, or after the fact kind of looking at it. But basically, we could see that if we decide the hypothesis is true, and it's actually true, then we will have come to the correct decision here. And likewise, if we decide that the hypothesis is false, and it's actually false, we've also come to the correct decision. And so these would be the likely outcomes that we're looking for here. The unlikely outcome, or not the likely outcomes, the ideal outcomes that we would be looking for here. Hopefully that happens, right? You make the right decision. But what I need us to understand is that sometimes, the hypothesis will be false. And it's possible that because of the data or the evidence that we collected from, say, 200 random samples of 50 rolls of a die, okay, we decide that it's actually true when it's false. And so what we're going to say is that this is an error. And what we're really trying to do, and the same thing down here, error, is minimize the amount of time that we come to the conclusion when it's true, when it's actually false, or likewise that we decide that it's false when, hey, that hypothesis might have been true. And so the idea really becomes this: can we use this evidence here and look at the proportion of our sample that came out to be a certain characteristic, and then maybe saying, based upon all of these samples that I did and the data that I got, does it suggest, the data suggest that what I got in my sample was a freak occurrence or to be expected? And so the whole idea of statistics will be to looking at a set of sample data and statistics and running some simulations, hold our claim, okay, up to our sample data and say, does our sample data support or kind of like not support, or I don't want to say reject, but not support our claim about the entire population of, say, rolls of a die 50 times. Cheers.